All right, so we were just talking about, well, I mean, we'll get back to the slides in just a second. I just wanted to talk about this, what we had just talked about, the large division between minerals. The vast majority of minerals that you find are silicate minerals, which of course have silicon and oxygen, silicon and two oxygens. All right, so anyhow, and that is further broken down into ferromagnesian and non-ferromagnesian. All right, so here are some examples. The ferromagnesian is biotite. There's some nice pictures of these. There's another one called hornblende and olivine. Olivine actually comes from the mantle of. I mean, any of these can be created. At different places, but we know that olivine is generally created in the mantle. All right, so and then of course for the non-ferromagnesian, we've got muscovite, plagioclase, which is another way of saying sodium calcium feldspar. Remember, feldspar is this huge. It's found. It's one of the silicates that's found all over the place. Almost as much as quartz. Actually, I think it's a little bit more common than quartz. And then this orthoclase, and that's potassium feldspar. So the K is just for potassium. So potassium feldspar, also known as orthoclase, plagioclase, which is also known as sodium calcium feldspar. All right, and then so we go over here to the other side. This is from your textbook. It's page 543. You got the non-silicate minerals. So we get carbonates, calcium, of course. I'm sorry, the carbonates, calcite. You got to say these right. Calcite. And then one of the sulfates is gypsum. Gypsum is, I think I mentioned this before, is something that you find in drywall, right? That's as part of what makes up drywall. If you ever put drywall up, that powdery substance is gypsum. All right, and then so we get down to remember, these are all non-silicates. Oxides. So one is a magnetite. Magnetite, of course, has a lot of iron in it, and therefore it's magnetic. One of the sulfides is galena. Looks like that. And then one of the halides is halite. Halite is common table salt. One of the phosphates is corundum, and then of course on the other side with the halites is also fluorite, which is we use small little bits of it to make toothpaste. Well, fluoride toothpaste. All right, and then here's of course the native element would be gold. All right, so that's. I just wanted to, but before I got back into these, the PowerPoints, I wanted to go over these nice pictures, and you'll see more of this in the lab if you haven't already had the lab on minerals. All right, so let's go back to this. All right, I gotta adjust this slightly. All right, so let me move it over. So here, I gotta pause. All right, that should be centered now. Very nice. All right, so in the last video we were talking about this question right there. Silicates are the most abundant, the most common and abundant mineral group because silicon and oxygen are they the hardest element? No, certainly not. We'll skip B because that is the answer. Found in the mineral quartz. Well, that is true, but that's not why. That's not why they're so common. Although quartz is almost half the rocks you come across, and they do form a tetrahedral structure. So really, the reason that they're so common and abundant is oxygen and silicon are the two in the Earth's crust. They're the two most abundant elements. All right, let's move on. Minerals formed by the process of crystallization. Okay, so we're going to delve a little bit deeper into this. So mineral crystallize in two primary sources. All right, so from molten rock and also from water solutions. That is, the water might precipitate. Precipitate means that when the water evaporates away, the material that's the substances, the minerals. I should stick with mineral. The minerals that had been dissolved in that liquid water now come out. That's what it means to precipitate. They precipitate out. All right. All right. So now we're thinking about it deep into the earth. Sometimes it's really deep into the earth. Sometimes it's not so deep into the earth. And so this is a general trend I want everybody to understand. All right. So minerals crystallize systematically based on their respective melting points. Okay. So melting. You have different melting points. Like so, you can have really, really high temperatures. Something that has an extremely high temperature for its melting point. Turns out that those crystals, that magma will crystallize first. So something with a really high melting point will crystallize, begin to turn into a solid before something that has a low melting point. And the stuff that has high melting points, when it begins to crystallize, they tend to be low in silica. All right, so low, silicon and oxygen. There's still some in there, but not as much. And the other thing that's important about this, let me finish this. So the last minerals to crystallize form from magma that have a lower melting point. And so because there's a lower melting point, you're going to have a higher concentration of silica. Okay, so I think a quartz, for example, which has a really high amount of silica, will be one of the last things to crystallize. Right. So what I was saying is, as the magma, so within an amount of magma, as the high melting point, the high melting point minerals crystallize first. The amount of silica it varies as the temperature begins to drop. Right, as the temperature begins to drop, you're going to get more and more silica available. All right, so water solutions are associated with later stages of crystallization from magma. These are what we would call deposits, right? Deposits of minerals that you find under the ground. When you're mining, and so here's what happens: the water basically becomes it becomes chemically saturated with the precipitants, right? In other words, if you have something that dissolves, when it's saturated, it means nothing else, no more mineral can dissolve in that water. Right, and so it's saturated. That's what it means to be saturated. You can't. There is actually a thing in chemistry called supersaturation, where generally you have to heat the substance. You got to heat the liquid, and you can put a little bit more minerals in there, or dissolve a little bit more when you supersaturate it. But we're not really concentrating on that. So ore deposits can be deposited into cracks and within the matrix of the rock. When we mine for stuff, a lot of times we will break apart the rocks and look for these deposits. I mean, that's because there's some minerals that are very, very precious. I'm not just talking about like gold and silver. All right. Water solutions can precipitate chemical sediments, such as carbonates and evaporites. All right. So for chemical sediments, solubility rather. So solubility is, how much, like if you put a mineral in water, how uh, how does it break down quickly, or does it take a long time for it to break down, right? All right, so okay, so low solubility means it's basically hard for these things, for these type minerals that are considered low solubility. It's hard for them to dissolve in water. High solubility, I'll give you an example of that I know for sure is high solubility, would be like salt. You put salt in water and it dissolves, it becomes soluble almost immediately, right? Assuming it's not saturated. If it's saturated, that means that it's taken the most amount of salt that it can possibly handle. So high solubility, it's easy for the thing for the mineral to dissolve in water. Low solubility, it's really hard. All right. So So as it says here, the low solubility minerals will precipitate first, right? And then the high solubility, because so high solubility, the mineral wants to stay in water. It wants to stay there more. This one, it does not want to turn. It doesn't want to become part of the water, and so this stuff will precipitate out first. And this one, the high solubility, will remain in water until the very end, until the water, the liquid water part, just evaporates away. Excuse me. Or so some of these have to do with like in caves they have stalactites and stalagmites where the water is dripping, and then whatever minerals are dissolved in the water will go to form. And we'll see a picture of that in just a little bit. They'll form these stalactites and stalagmites that the stalactites hang down, stalagmites grow upward, right? Because there's this there's minerals that are in the water. They have solubility. All right, so let's look at this next one. In the crystallization of chemical sediments from a water solution, low solubility minerals precipitate first because, okay, so why do they precipitate first? I kind of just went over that, but let's just look at this. They just dissolve more easily. No, the low solubility it's very hard for them to that's why they're low solubility. So A is not right. They're more susceptible for being dissolved. No, that means this. In other words, that would be high solubility. They are not easily dissolved, right? That's the okay. They are infinitely soluble. I don't even know what D means, but so C would be the answer, right? That because they're low solubility, they're not easily dissolved in water. All right, so there it is. All right. Oh yeah, I'm running out of time here. All right. So this is the next video. We're going to take up rocks. 3 types of rocks: igneous, sedimentary, and metamorphic. Okay, so we're going to investigate. Remember, rocks are formed from minerals. That's a very important idea in chapter 20.